In section 1.7, we're looking at depreciation and the slope-intercept form of the equation of the line. We're going to interpret slope as the average rate of change. We talked about the average rate of change in section 1.6. We're going to talk about that in terms of slope. We're going to use the formulas to determine slope again, talk about practical meaning of the vertical and horizontal intercepts, and developing the slope-intercept form of the equation of the line, and then using that form to get our vertical and horizontal intercepts, and then talking about the definition of zeros, what those zeros of a function are. All right, so in our first situation here, we decided to buy a new Honda Civic, but we're concerned about the value depreciating over time. So we've researched and discovered that the suggested retail price is $22,905, and it's going to depreciate at a rate of $1,750 per year. So I'm going to fill in this table with the value of the car. So initially, after 0 years have gone by, so when you first buy the car, we know its value is $22,905. But every year, it depreciates by $1,750. So if we subtract 1,750, we'd get down to 21,155. So we're just subtracting off 1750 to depreciate by 1,750 to get to the next value. After 2 years, we're going to depreciate again. So if I subtract another 1,750, that's going to bring us down to 19,405. And again, after the third year, I'm going to depreciate again, subtract off another 1,750. That's going to bring me down to 17,655. Now, notice that they don't go to year 4 next, they go to year 5. So I'm going to have to subtract twice to get to year 5. I'm going to have to subtract 1750 times 2 to subtract down to year 5 from year 3. I have to subtract it once for year 4 and once more for year 5, so 2 times. So if I subtract off now twice 1750, that'll drop us down to 14,155. Notice again, I don't go to 6 or 7, I go to 8. So I'm going to have to jump all the way down to 8. I'm going to have to subtract that 750 3 times now to go from 5, 6, 7, 8 to go up to 8. And that would bring us all the way down to 8,905. All right, now part B, is the value of the car a function of the number of years of ownership? It is a function because for each input, there's precisely one output. There's not a question of, well, after 3 years, was it 17,655 or was it 18,655? There's no question. It was 17,655. So there's a process for us to compute the value after a certain number of years. So yes, it's a function because each input has exactly one or precisely one output. Or one unique output. Exactly one or one unique output. What is the input? What is the output? So the input, my choices of variables are years and value. My table is organized. Most tables are organized in input, output. So I'm going to label those up here. Input we would like to see first. Output we would like to see second. It's possible that a table would be misorganized, but for this particular case, input being the years, that's our independent variable, and then the output, the value, depends on how many years old the car is. So our input is going to be years, and our output is going to be the value. Remember, the input matches up with independent variable, and output is a dependent variable. Select 2 ordered pairs of the form n, v from the table and determine the average rate of change. So any 2 will do. I'm going to start with the first ordered pair, 0, 22,905, and why not the second one, 1, 21,155. And it wants me to compute the average rate of change. So the average rate of change, we take the difference in outputs with final output minus initial output. So 21,155 minus 22,905 over final input, 1, minus initial input, 0. So if I subtract these, if you take 21,155 and you subtract 22,905, you should be getting negative 1,750 divided by 1 minus 0 is 1. And if you finish the division, you'll get negative 1,750. So the average rate of change between the first two ordered pairs is negative 1,750. What are the units of measure? The units of measure are in output units per input units. So at first we'll have our output units, which are in dollars, per input units, which are in years. So what is the practical meaning of the sign of the average rate of change? The sign is the fact that it's negative. It's a negative 1750. That's our sign. And the sign means that it is decreasing or depreciating by $1,750 per year. So it signifies a decrease or depreciation in value, just two words for the same thing in this case right here. Now we're going to select two different ordered pairs and compute the average rate of change. So this time, how about I select the 3 and the 5? So 3, comma, 1,700, sorry, misspoke, 17,655. And then 5, comma, 14,155. And again, we're going to compute the average rate of change in output over change in input. So change in output, we have our 14,155 minus our 17,655 over our 5 minus 3. I'm going to grab decimals to help me with the difference here. So if we do the difference on the top, our 14,155 minus our 17,655, that gives us negative 3,500 divided by 5 minus 3, which is 2. And if we finish the division, we will get negative 1,750. Okay, so we should note right away that we got the same thing as when we did the average rate of change between the initial point and the point after 1 year. We got the negative 1,750. When we picked two other ordered pairs, the computation was certainly different. When I divided and simplified, the result is the same. We get to do it one more time. We're going to pick another set of ordered pairs. You can choose any of the ordered pairs that you want. I'm going to choose the bottom two. So I'm going to choose 5, 14,155. And I'm going to choose 8, 8,905. So we skipped over a couple of years. We're going to compute the average rate of change here. Final output, 8,905, minus initial output of 14,155 over final input 8 minus initial input of 5. And again, I'm going to use Desmos to help me with the computation. So here, we need to do 8,905 minus 14,155. That comes out as negative 5,250. And we're going to divide that by 8 minus 5, which is 3. So negative 5,250 divided by 3, it's negative 1,750 again. So once again, the same answer that we had gotten no matter which of the two ordered pairs we had chosen. The computation came out differently in the intermediate steps, but once we finish the division, we have that same value again. All right, so our conclusion in part D, what can we infer about the average rate of change over any interval of time right here? It's going to be the same, right? It's going to be the same over any interval. And the value that it is the depreciation rate that we were given up at the top. Let me get rid of my decimals window here. It's our depreciation rate. So this value up here, because we were using that to calculate the value, that value is the depreciation rate. That is the amount lost per year. So we should have expected that we would have gotten the same. All right, over to our next page with our definition. Anytime that you compute the average rate of change between any ordered pair and it's constant, you get the same thing, then the type of function that you have is going to be a linear function. Not all functions are linear. Some functions have different rates of change depending on which values you can compute them from. We saw that up on section 1.6. But if you have a constant, if you have the same thing for your average rate of change, no matter which ordered pairs you choose, your function is going to be linear. So, explain using the definition of linear function if the value function is linear. So yes, it is linear because the average rate of change is constant. The average rate of change is constant. Is this function increasing, decreasing, or constant? It's decreasing. It's just decreasing because our average rate of change was that negative value. We already mentioned that it was decreasing or depreciating, and the reason is that our average rate of change was a negative number. All right, so we're going to graph. Most of the time when we get to this kind of graph, we want to see the picture. We're going to graph it in decimals. So I'm going to do that. I'm going to graph this one not by hand, but in decimals as a table. Okay, so I'm going to delete some of these lines right here and insert my table. And for our inputs, we have 0, 1, 2, 3, 5, and 8. I need to go ahead and type in the outputs from our table. And once the table has been completely entered, we can zoom over on the data with the Zoom Fit button at the bottom. We can see the data here. So as we know from when we found the data that the first several values were evenly spaced just 1 year apart, then we skipped year 4, went to year 5, we skipped 6 and 7, went to year 8. But we can still see the linear pattern that if you use a ruler, you'd be able to smoothly connect all of your ordered pairs. You can even see exactly where the missing one should have been. The missing one should have been based on the imaginary line that you would draw. All right. So this is our line. This is our dots. It would be fair to connect these in this graph right here. It's going to be a continuous function because the value will depreciate mid-year as well. It's going to not just change where for the entirety of year 2, it's worth the same amount, and then poof, on year 3, oh, aged out, it's worth less now. It actually depreciates a little bit each day, so it depreciates in between, so we can imagine these being connected. So I'm going to draw just a really rough sketch of what this looks like over here. We're seeing our points like this, and we would imagine connecting them. And of course, if we were drawing it by hand as our only method of drawing, we'd be a lot more careful to make sure that we were scaled and labeled. But we're using decimals for the majority of our graphing purposes. All right, definition down here at the bottom of slope. So the slope is the constant average rate of change. So they're actually calculated the same way. We only use the word slope in the context of linear functions. We can use the phrase constant average rate of change whether or not it's linear. Or, sorry, we can use the phrase average rate of change whether or not it's linear, because any 2 points will have an average rate of change. But if it happens to be constant, where several different points have the same average rate of change, we're going to refer to it as slope. and it's going to be the slope of a linear function. So the way it's computed is the same way average rate of change is computed. It's the change in y divided by the change in x, or change in output divided by change in input. Change in output is computed with the final output minus the initial output, divided by change in input computed by final input minus initial input. So this is the same formula that we would have seen for the average rate of change. If it's a constant, we can refer to it as slope. All right. Next page. What is the slope of the line graphed in problem 4? Well, I already know the average rate of change, and so I know that they're the same, and so I know that it's negative 1,750. What is the relationship between the slope of the line and the average rate of change? They are the same, but we will note that the average rate of change has units associated with it. So anytime I talk about average rate of change, I want to think about the units that go along with it. Slope does not necessarily have to have units, depending on if you're in a contextual situation or a non-contextual situation, but they have the same value. So I'm going to put this word over here as well. The same value, same numeric value. The units could be present in an average rate of change are not necessarily present in the slope. Now, the practical meaning of the slope, that's really getting into the average rate of change with our units. And so we're going to write our sentence of the value of the car is, what's it doing? Increasing or decreasing? It's negative, so it's decreasing. Or decreases. By how much? 1,750. I don't say the negative right here because I already said the word decreasing, which absorbs it. Units, dollars, and then per, what are the x units? Year. So the important aspects of this sentence, when you're going to explain a slope, the format for slope, I'm going to write over on the edge because this is just really important. They're always of the form the output is, and then it's increasing or decreasing by, then it's our value for slope, and then it's our y units, or our output units, per our x units. So the output, the value of the car is what? Decreasing by how much? Our value. Y units, you could write the word dollars here. Dollars are the only kind of unit that actually goes in front of the number, so we put our dollar sign over here, but you could write the word dollars instead afterwards. Per X units are here. So all of those aspects need to be in your sentence. This is the generic setup for how do I explain a practical meaning of a slope. Just need to substitute in what the output is, increasing, decreasing, value, units, and X units. All right. Now, on to the next part here, looking at the vertical intercept. Sometimes the vertical intercept is called the y-intercept. It just depends on if your vertical variable is y, or maybe it's v, and it's the v-intercept. So it doesn't matter what letter you're using. Vertical intercept is the more general name, and y-intercept, thinks about y being the vertical variable. The vertical intercept is where the function crosses the vertical axis. So if I cross the vertical axis, scooch, then I have no width. We're right there on the vertical axis. It means that the x coordinate is going to be 0. So it's 0 comma a number, 0b or 0y, depending on what you're calling the letter for the value there at the intercept. Okay, so use the table of data for problem 1 or the graph to determine the vertical intercept. From the graph, I should probably use my data right here. I need to have that 0 for the input to find the vertical intercept. So it's going to be 0, 22,905 here. I can also determine this from the graph. If I look at my decimals graph, where it's actually properly scaled, I can see I touch the y or vertical axis at 0, 22,905. So I can see it both graphically and numerically through the table. Where the input is 0, I touch the vertical axis. So onto that page, next page, we can note to ourselves that the vertical intercept is 0, 22,905. What is the practical meaning? So we always need to explain the practical meaning and tell what the 0 means and what the 20,905 means. This 0 corresponds to initially, or 0 years after the car was purchased. The car was worth, and then we have our value here, $22,905 with its units. So I don't have to write the 0 itself right here, but I need to explain what that 0 means. It means initially, brand new car, no time has gone by, when the car was new, lots of different words you could put in there. I just could put in the word initially to capture what the 0 stands for. All right, next, number 7, review how we determine the value. All right, so we know that when we determined the value, we started with the 22,905, and then we subtracted the depreciation rate of 1,750 for the first year, the second year, the third year. We kept subtracting this value. So we subtracted it n times, where we plug in n equals 1 or 2 or 3. We subtracted it this many times. So that would be our function. We also know that this is our slope. So this is the one that's going to be changing as our number of years increase. Now we want to graph this and see how it compares with the data points. So back over to Desmos, I'm going to type in this function. So V equals 22,905 minus 1,750 n. And we should notice that the line goes through every one of our points, and this line would help us make the prediction for 4 and 6 and 7, the ones that were not captured in the table, but we could still have computed them, and we can see that this line goes through what those points would have been as well. Now, this stuff down here in the book, this X min, X max, and Y min, Y max, this is help on how to set up your window. I didn't need it this time because I had already typed in the window and done zoom fit to be able to see the data. But if I had been in the home window, I would not have seen anything had I entered this. So they're giving us a little bit of help here to scale our window. So I'm going to scale my window with this help using the graph settings button. It tells me that the minimum value of X should be set to be -2. The maximum value for X should be set to be 16. The minimum value for Y should be set to -500. And the maximum value for Y should be set to 25,000. So as you can see, if I use the scaling that they have suggested, it gets me into a window where I can view the data points and where I can view the equation. So in particular, what was very much important to this situation was that large output value, that large Y max value. It's so large, I would have had trouble just using the scroll wheel to scroll that high to get to be able to see the graph in this window. The other thing is if I use the scroll window, it scrolls in and out on X at the same time, and I really don't want X scrolled out very far. I want Y scrolled out a lot further. So having a manual way to reset our window is very helpful. So that's what they were trying to share with us there. Now, how does this graph compare with our graph in problem 4? So we should just be observing that the graph of the line matches the graph of the data very well. So we'll make a note that the line fits the data very well. It's a little bit too loose, so we're going to say exactly. It's even better than very well, and it does fit the data exactly in this case here. All right, recall that the slope of our line is m equals -1750, and the vertical intercept is 0, 22,905. How is this information contained in the equation that we see? So in our equation, I'm just going to write it down again so that we can draw around it. We have our 22,905 minus our 1,750 n. And as pieces of this equation, we see that our slope value is right here with our variable. and our vertical intercept is the other number that does not have the variable. Looking at the bottom of the page, tip my camera a tiny bit here. There we go. The bottom of the page, we see that lines can be written in slope-intercept form as either y equals mx plus b or y equals b plus mx. In either case, m, the slope, is the number with the variable. So I have my variable n, and I'm in this form right now because my slope is with the variable. I could have written that part first and had the slope with the variable first. And the number that is added on is the vertical intercept. Mine happens to be right here. Could have put it at the end and it would have been just the same thing. Okay. All right, next, looking at these equations, we want to identify the slope and the vertical intercept from the equation that's given. So I know if my equation is in the form y equals mx plus b, I can read off the slope and the vertical intercept as the coefficient of x and the constant respectively. So my slope m, well, there's x, so -2 is our slope. And then the vertical intercept. Now, it's going to have 5 in it, but don't forget that an intercept is an ordered pair, so I'm actually going to write this as 0, 5. 5 is the value that goes into the vertical intercept, but I do want to put it in full ordered pair form. The vertical intercept is 0, b, as shown in the previous page, is 0, 5 in this case. Right, so continuing. The slope is the coefficient of the variable. The variable is t. Its coefficient is 3/4. And the vertical intercept is 2 is the value, so 0, 2. All right, next we need the slope and the vertical intercept. Now, this time it's written backwards, so it's written so that the vertical intercept is first, because this 2 does not have a multiplicative variable. The slope and the variable are going to be here at the end. So I'm going to do my vertical intercept first with this 0, 2. And then the slope, since there's -1r here, it's -r, I'm going to read that -r as -1r. And so -1 is my slope. I can't use the letter r in the slope. I need to know how many r I have there. If it says -r, I have -1r, so -1 is the slope. Okay. And the last one for our slope and our vertical intercept. The vertical intercept comes from this 5/6 because it does not have a variable. It's just the number, so 5/6 is part of our vertical intercept. And for the slope, again, when I have just a plain x, it's a 1x. And that 1x is divided by 3. So I have 1/3 for the slope. That's the full numeric component of that term. 1x over 3 is 1/3 x. 1/3 is the numeric part. Take the variable off the side there. So I can look at an equation if it's in slope-intercept form, and I can read off what the slope and the vertical intercept are. All right. Now I can also use that information to sketch a quick graph of the line. So in this first one, we said that the vertical intercept was 5. These are the same equations from the previous page. You can look back, but our vertical intercept is at 5. So I can draw a dot right up there at 5 on the y-axis or the vertical axis. And my slope is -2. I know that -2 is -2 over 1, so I can count down 2 over 1 to get my next dot, down 2 over 1. And I'm just going to, by hand, do as many as I can, so it makes it easy to connect these. It's easier to connect without a ruler if I have a lot of dots to connect. If I was graphing this on MyMathLab and I wanted to enter this graph, I would graph just the first one, and if I counted down 2 over 1, when I click on the next dot, the rest is going to automatically connect. So I just have to have 2 dots, and it's going to automatically connect for MyMathLab. By hand, I just do a few more of them, so it makes it easier for me to trace my line. Okay. Next one, we said that the vertical intercept was at 0, 2, and my slope is 3/4. So again, when you see 3/4, we saw this negative 2 over 1, that was 2 down and 1 over. This is going to be 3 up because it's positive, not negative, right? And then 4 over. And it's over to the right in the positive direction because it's a positive 4. So 1, 2, 3 up, 1, 2, 3, 4 over, 1, 2, 3 up, 1, 2, 3, 4 over. Now, I could also have thought of this as being negative 3 over negative 4. In that case, it would have been down and left. Just want to show that's going to line up because 2 negatives make a positive. So if I went down 3, 1, 2, 3 over 1, 2, 3, 4 backwards, this point is also going to line up. So I can think about this. Usually we'll count the up 3 over 4 to the right. I could, though, go in the opposite direction to get more points and just help me make my line, help me make my connection. So down 3, back 4 works just as well. All right, we decided that the vertical intercept for this one was also 2. And remember that your slope was negative 1. And so that's going to be negative 1 over 1. So down 1 over 1 in the positive direction. Down 1 over 1. Down 1 over 1. Or you could think about this as 1 over negative 1. Because again, 1 negative stays negative. In which case this would be up 1, back 1. So you can go backwards as well. And you see that those all line up, so we can trace our line. And in the next one, this one has 5/6 as its vertical intercept. 5/6 is just a little bit below 1. And my slope is going to be up 1 over 3. When I go up 1, I'm at 5/6 high, so I'm going to land at 1 and 5/6, then over 1, 2, 3. So I'm not landing quite on a 1 whole unit up. If I start up 5/6, I end up 1 and 5/6. I can still count up 1 over 1, 2, 3, just landing at 2 and 5/6 and so on. And then I'm going to connect these and see our graph. A little bit more of a pain when I have that fractional y-intercept, but it certainly can be done. All right, so next we're going to talk about horizontal intercepts. So the horizontal intercept is where your graph crosses the horizontal axis and it has no height. So the y value is going to be 0. The output value is always 0 for a horizontal intercept. They're also called X intercepts if we name the horizontal axis X, but it could be T or C or whatever your input variable is called. So general is horizontal intercept, or X intercept in the specific case where we call the horizontal variable X. So it's usually written in the form a comma 0. What's important to note, whether you call it a or X, is that the y coordinate is 0. All right. So we have a couple of questions and examples here. I'm going to flip to the next page, number 11, where we get to do a question. You can read through the example before this if you want to pause and look at the example. When I get to number 11, we're going to determine the vertical and horizontal intercepts, and we're going to use them to graph the equation. I know the vertical intercept because that comes from the b value. So 0, negative 6 is our y-intercept, our vertical intercept. I don't know the x-intercept from the equation, so I've got to go find it. The x-intercept comes from setting the y value equal to 0. So I'm going to plug in 0 equals our 2x minus 6. I'm going to add this 6 to both sides. 6 equals 2x. And I can divide both sides by 2 to get 3 equals x. So my x-intercept is 3, 0. So I can graph this at 0, negative 6 and 3, 0. And I can just go ahead and connect those 2 points to see the line. So there's 2 ways to graph. I can graph by both intercepts, or I can graph by counting the slope up and over until I complete my line. So we're going to do the same thing for this next one. I know that the vertical intercept, or y-intercept, comes from the value that's not tied to x. So my y-intercept is 0, 4. Now, if you think about it, when you plug 0 in for x, if you plug 0 in for x, y equals 4 minus 0, that's 4. So we are doing a computation x equals 0 to get the y-intercept. It's just I can do it so fast because it's always going to be the b value, because if you put a 0 in for x, you're going to get the b value. The x-intercept, not so fast to calculate. So if I calculate the x-intercept and plug in y equals 0, I have 0 equals 4 minus x. I'm going to add x to both sides just because it's already negative. Might as well make it positive on the other side. And I get x equals 4. So our x-intercept is 4, 0. Now we can graph this at 4, 0 and 0, 4. And we'll be able to connect our points. All right, number 12, I think this is our last example. Converting Celsius to Fahrenheit. The temperature on a warm summer day might be 27 degrees Celsius, and your refrigerator is set at 5 degrees. Set your oven to 180 to cook a turkey, and if these temperatures seem strange, it's because they're measured in Celsius. Right. 27 in Fahrenheit is quite cold, but in Celsius, it's warm. All right, so we're going to convert between Fahrenheit and Celsius. We use the equation that 1.8 times the temperature in Celsius plus 32 equals the temperature in Fahrenheit. So we're going to use this equation to complete this table. I'm going to get Desmos to help me autofill this. Let's open. I'm just going to start a new graph. And I'm going to write it as a function. So I'm going to do f of c equals 1.8c plus 32, and then start my table. And I'm going to do f of, and we're going to have it plug in the x ones into the f function. So the temperatures are -10, 0, 5, 10, 27, and 100. All right, so if we write these in, at -10 degrees Celsius, it's still 14 degrees Fahrenheit. At 0 degrees Celsius, it's 32 degrees Fahrenheit. At 5 degrees Celsius, it's 41 degrees Fahrenheit. At that 27 degrees, it's 80.6. So yeah, it's nice and warm. 27, oops, I missed something. I skipped 10. 1050. I was busy with 27. That's 80.6. So 10 degrees, 50 degrees, a little chilly. And then 100 degrees, that's our 212. So that's when water boils in Celsius is at 100 degrees and boils in Fahrenheit at 212 degrees. All right, so next we're going to sketch a graph of those ordered pairs. Nice thing about putting them into Desmos is I can do my zoom and fit to see them right away. And I already had graphed the function, so I can see the line on the graph already. I'm going to make a quick sketch of this. What we should know about this is that I do have a couple points that go past the x-axis because temperature can be negative. So when I sketched my graph, I wanted to show that some points were past the x-axis, and then way over here, our furthest point was over there, so there's quite a bit of gap. They line up in a straight line. Okay. Now, determine the average rate of change as temperature increases from 0 to 100 degrees. Okay, so the points were at 0, we had 32, and at 100, we had 212. So I want to compute the average rate of change in output, 212 minus 32 over change in input, 100 minus 0. So 212 minus 32, let's go ahead and do the computation. That's 180 divided by 100 minus 0, which is 100, and 180 divided by 100 is 1.8. What is the slope of the line? So the slope of the line is 1.8. And how does this compare to the average rate of change? Same thing. Now, perhaps I should have recognized this a separate way. Instead of saying that the slope was the average rate of change and knowing that they were the same, I should have looked back up here and identified the slope as part of the function as the variable's coefficient, 1.8. And so then I can say it's the same thing as what I computed. That's probably what they were asking me to do, is not just say, I know average rate of change is equal to slope, but notice that this is the slope, and therefore it's the same as the computation of the average rate of change. Okay. Is your function increasing, decreasing, or constant? It is increasing. I can see that both in the graph, because it's going upward, and because the slope is positive. I know it's increasing. Determine the vertical and horizontal intercepts. I already know one of them because I had an ordered pair 0, 32, and I can see 32 in my equation. So I have 0, 32. And then if I plug 0 in for the output variable, f in this case, equals 1.8c plus 32, I'll be able to solve the horizontal intercept. Got to divide off the 1.8. And let's see what we get from negative 32 divided by 1.8. Negative 17.8. All right. So the horizontal intercept is at negative 17.8, 0. We're going to verify our result now using the graph. So back over to my Desmos graph. If I turn the line back on up here, I can click on the vertical intercept at 0.32, and I can click on the horizontal intercept right here where I cross the horizontal axis at negative 17.778. I rounded it to one place when I wrote it down, negative 17.8. Again, we can confirm those two values graphically. What is the practical significance of each intercept? All right. So the input variable is degrees Celsius. So the vertical intercept means that 0 degrees Celsius is equal to 32 degrees Fahrenheit. And the horizontal intercept means that negative 17.8 degrees Celsius is equal to 0 degrees Fahrenheit. When does F equal C? I don't know yet. Okay, so I'm going to use my margin again. I just don't have enough space to write over here. So, my margin for when F equals C. So in the equation, F equals 1.8 C plus 32. Instead of F, I'm going to plug in C. So I have F and C being equal, being the same letter. It doesn't actually matter what letter. I could make them both Fs or both Cs. So I'm going to subtract 1.8 C from both sides. That should get me negative 0.8 C equals 32. And then I'm going to divide by 0.8. So that gets me, let's find out. If I take 32 and divide it by negative 0.8. Oops, goodness. Gotta get my keyboard moved out of the way so I can hit the right buttons here. There we go. All right, so it gives me negative 40. Okay, so that should mean that the ordered pair is negative 40, comma, negative 40. So that should mean that negative 40 degrees Celsius is the same thing as negative 40 degrees Fahrenheit. And we're going to check this graphically. So on our graph, if we graph the ordered pair, negative 40, comma, negative 40, hopefully that ordered pair shows up on our line. It does, it's on our line. So negative 40 degrees Celsius and negative 40 degrees Fahrenheit are the same temperature. Kind of cool. Pretty cold, either way. All right, last, we have zeros of a function. So we're going to look at the definition of zeros. So a value a is a zero of the function if f of a is equal to 0. In other words, a zero of a function is the input value that makes the output 0. So the input is the 0 because it makes the output 0. All right. So number 13, if the value 3 is a 0 of the function, then f of 3 is equal to 0. Write the ordered pair corresponding to f of 3 equals 0. The input is 3, the output is 0. So if that's true, f of 3 equals 0, then the ordered pair is 3, 0. Describe the location of this kind of ordered pair. Okay, so 3, 0 is going to be an X-intercept. All zeros correspond to X intercepts. So the two phrases can be used interchangeably. We can talk about zeros or X intercepts. So if f of a is equal to 0, then x equals a is the 0. Says it over here. A is the 0. X equals a is the 0, and a comma 0 is the X-intercept. So the a value is called the 0, or the ordered pair is a comma 0 is called the X-intercept. Determine the 0 by setting the equation f of x equals 3x plus 12 equal to 0 and solving for x. So 3x plus 12 equals 0. We're going to subtract 12 from both sides. 3x equals negative 12. If we divide both sides by 3, we'll get x equals negative 4. So x equals negative 4 is the 0. And that means that the X-intercept is negative 4, comma 0. So there's a relationship between the two. They come from the same value. They're just displayed differently. One is an ordered pair, and one is just our value.